Imagine this, the teacher says. Alex is revising for the IB physics exam late at night. Alex takes a glass of crushed ice straight out of the freezer and leaves it on the table in a warm room. Then Alex walks away for an hour. When Alex comes back, something feels wrong. The ice did not warm up, but for a long time the temperature didn't change at all. Alex frowns. Wait, if the temperature stayed the same, does that mean no energy was added? This is the moment when many students panic in the exam. Alex almost did too. And Alex realizes the key. Temperature measures average kinetic energy, but during the melting, energy is being used to break the bonds, not the raise the temperature. Same temperature, more internal energy, and suddenly that strange behavior of the ice makes a perfect sense. Yes, now let's come back to the crushed ice situation, and we are going to apply that knowledge in this particular question. This is an IBDP question, a paper 2 type of question where you are going to see a graph and understand what's happening here. Now, this is a thermal physics question. Let us look into this question very clearly. A crushed ice of mass 50 grams at a temperature of minus 15 degrees Celsius is placed at a warm temperature. The graph shows the variation of the temperature T of the ice water system with time. So as you can see the graph here, I have a temperature in the y-axis and I have time in minutes in the x-axis. Now using the graph, calculate the average thermal power supplied to the ice while the temperature increased from minus 15 degrees Celsius to 0. The specific heat capacity of ice is given. Now look carefully. What are they asking us? They are asking us the average thermal power. What can I find from here? They have given me a specific heat capacity of ice, and that is 2100 joules kilogram per kilogram in Kelvin. And they have given me the change in temperature, that is minus 15 to 0. So obviously, what is the change in temperature? Delta T is equal to minus 15. Delta T is equal to minus 15. Now you might think, what if it is in Kelvin? So right now it is given in Celsius. What if I had in Kelvin? Will my delta T be same? Yes, your delta T is going to be same because K is the Kelvin is nothing but you just add 273.15 in front of it. So the difference is going to be same here. So the delta T value is 15, right? So that is 15 Celsius I can take. Now if it's Kelvin, it's 15 Kelvin or 15 Celsius. If it is Celsius, it is 15 Celsius. Now I have the mass of the ice given, that is 0.5. So that is 50 grams. So 50 grams is going to be 50 into 10 power minus 3 kilograms, right? To be in safer side. See, if you are confident enough that you're going to divide by 1000 and get a proper answer, you do it, or multiply it with 10 power minus 3. Anything works. You can multiply it with 10 power minus 3. That is also fine. Okay. Now I have these values. I need to find the energy. Okay, I need to find the energy. Q is equal to mc delta T. So what is the thermal energy required for this? And yeah, this is a formula which I'm going to use to find the energy in this case. And to find the energy, I'm just going to do 50 into 10 power minus 3 into 2100 and into 15. So you see, approximately I'm going to get my answer here. If I multiply all these, I'm going to get my answer as 1575 joules. So the Q value comes around 1575 joules. Now this is the energy required to change the temperature from 0 to minus 15, minus 15 to 0. So that is this particular region, students. Remember, specific heat comes only during the change in temperature, and this is the change in temperature that is happening, minus 15 to 0. So what kind of heat was used here? It was a specific heat that was used here, and the total energy required for this phenomenon for this situation is 1575 joules. Now, obviously, you know that power is equal to energy by the time taken. Now, the time taken to this for this to happen is 5 minutes. Do not put it as minutes, you try to put it as seconds, right? So 5 minutes is 300 seconds. So I have energy 575 by 300. So approximately the power is 5.25, I guess. 5 1575 by 300 is 5.7, sorry, 5.25 it comes. Watts. What is the unit of power? Unit of power is watts. Sorry about the cough. I'm very, the change of climate has made me a little sick. Okay, but still I wanted to record a video today, or else I will be lazy. If I don't record a video, I'll become lazy. So I just recorded this video, no matter what. And to please do subscribe. Please do subscribe for this. I'm making a video when I'm sick, so I deserve a subscription, isn't it? Okay, jokes apart. Let's go to part B. During the time for which the temperature remains constant at 0 degrees Celsius, the ice is melting. Use the melting time shown in the graph, and in your answer in part A, estimate the specific latent heat of fusion of ice. Right? So they are asking me specific latent heat for the fusion of ice. Now look clearly here. From 5 to 55, this is the time. Okay, from 5 to 55, what's going to happen here? I'm going to have a change in state, right? Why? Because the temperature is not changing. The temperature here is not changing. So that's why I'm saying that I'm having a change in state here. Okay. So it's a change in state. So I am going to look for specific latent heat of fusion. I'm going to find specific latent heat of fusion. So my time is given here, and that's time is going to be 50 minutes. 50 minutes, of course, when I'm doing calculation, I have to convert it to seconds. So right now I have 50 minutes. So that's going to be 3000 seconds, right? Yes, 3000 seconds. 3000 seconds. Okay. Now you know that the latent heat formula is Q is equal to ml. And here they're asking me to find the L value, because I know that at 0 degrees Celsius, it is a latent heat. Temperature won't change. It's a latent heat. I know the mass. I need to find L, but I don't have Q. What I know is that I have time. But look at the question A. The average thermal power supplied. So I have the power supplied with me. So here, the power is being supplied here. Okay. The power is being supplied with some instrument, maybe a water heater, maybe. Okay. The power, it is being supplied here by some heater, and this is the power. Now this is the same power that runs for even this 300,000 seconds. So here energy is equal to power into time. I have my power, which is 1575. I have my time, which is 3000. So the power into time is approximately going to be 1.575. Yes, somewhere around 1.57. 1 second. Yeah, if I do the calculation, the power supplied, sorry, I'm, my bad, that this is energy. The power is 5.75, students. 5.25, my bad. 5.25. Yeah. So now when you multiply this, okay, when you multiply this, you are going to get somewhere around 15750. Yes, 15750 joules. 15750 joules. This is my power and this is my time. Okay. power into time, this is the energy. So I can substitute that energy here. So 15765 equal to, mass is already given to me, and that is 50 into 10 power minus 3, and L is what I need to find. So L is equal to 1576756 divided by 50 into 10 power minus 3. So using this equation, I'm getting the latent heat value. Okay, so that comes around, if I do the calculation, it comes around 3.15, range of 3.15 into 10 power 5. And the unit would be joules per kilogram. Joules per kilogram. Why? Because Q is equal to ml. So L is equal to Q by m. Q is joules, m is mass. So joules by kilogram. So this is a specific latent heat that I am getting, and you are getting the latent heat of this particular region. Now you got from 5 to 55 minutes, right? So you have got the specific heat of the time when the temperature was changing. You got the latent heat for the time when the temperature was not changing. But what was happening? The phase was changing. Ice was becoming water here because heat is being given. So ice was becoming water here. Understood? Now, between 5 to 55 minutes, the solid, ice, and liquid coexist at 0 degrees Celsius. That's true. At 0 degrees Celsius, when the ice is melting, you have liquid and you have ice also together coexisting at 0 degrees Celsius. So remember, in a phase change point such as a freezing point or a boiling point, two phases coexist at the same point. So compare the internal energy of 1 kilogram of solid ice with internal energy of 1 kilogram of liquid. So they're asking whose internal energy is bigger at this point. Now let me tell you, students, remember, the average kinetic energy, students, is dependent on temperature. 3 by 2 kT. Remember, energy is equal to 3 by 2 kT. Now students, this is the kinetic energy. This is the kinetic energy. Kinetic energy is 3 by 2 kT. Okay. So average kinetic energy is proportional to temperature. Now since the temperature at this point is 0 degrees Celsius, so for both the ice and the liquid, the water, the kinetic energy is going to be same at that point. But it is the potential energy that's going to be different. Okay, that's going to be the potential energy that's going to be different. So remember, liquid has higher potential energy. Liquid has higher potential energy at this point. Remember, liquid has higher potential energy. Solid has lower potential energy. Remember, in terms of potential energy, you can make a note of this point in terms of PE. In terms of PE, gases have the highest PE, students. Gases have the highest PE and solids have the lowest PE. Solid have the lowest PE. So that's about this particular question. I hope you learned few things from this particular question. It's a small question. It will be available with me. I will try to put it in the description. Right? This is a very simple question of thermal physics, understanding the specific heat and the latent heat. Please subscribe for more videos on IBDP, IGCSE, and AS level, and of course IBMYP also. So I will be trying to cover all the difficult concepts through my videos so that it is really beneficial for you in the exam times. And yeah, please do learn. This physics revolution is for you to learn and become a part of this physics revolution by subscribing to this video or subscribing to this channel. So see you later next week. Bye everyone.